In 2023, Boeing and NASA stood in front of the press and unveiled what they called the future of flight, a radical new aircraft shape that looked like nothing the industry had ever mass-produced. Ultra-thin wings braced by diagonal struts, a silhouette that belonged more in a wind tunnel than on an airport tarmac. They called it the X-66A, the Sustainable Flight Demonstrator. The promise was staggering. Up to 30% less fuel burn than the best narrowbody jets flying today. If that number holds, it would represent the single largest leap in fuel efficiency in commercial aviation since the dawn of the jet age. Airlines were intrigued, environmentalists were hopeful, regulators were watching, and Boeing desperately needed a win. But here's the problem: the very thing that makes this aircraft revolutionary is the same thing that might kill it. Because the X-66A doesn't just challenge the laws of aerodynamics, it challenges the physical dimensions of every airport gate on the planet. And in commercial aviation, you can have the most efficient wing ever designed. If it doesn't fit at the gate, it doesn't fly. This wasn't just about building a better airplane. It was about whether the entire global aviation infrastructure could be rewritten to accommodate one. To understand why the X-66A exists, you have to understand the crisis that summoned it. The commercial aviation industry is responsible for roughly 2 to 3% of global carbon dioxide emissions. That sounds small until you realize it's growing faster than almost any other sector. By some estimates, aviation emissions could triple by 2050 if nothing changes. And the industry knows it. In 2021, the International Air Transport Association committed every major airline on Earth to a single target: net zero carbon emissions by 2050. That's not a suggestion, that's a deadline. Miss it, and the industry faces carbon taxes, route restrictions, and a public relations catastrophe that makes the 737 MAX crisis look like a footnote. So what are the options? Sustainable aviation fuel helps, but it's expensive and supply is nowhere near where it needs to be. Hydrogen propulsion is decades away from anything resembling commercial viability. Electric aircraft can barely carry 9 passengers 200 miles, let alone 180 passengers across a continent. The math doesn't work. That leaves one lever the industry can actually pull right now: aerodynamic efficiency. Burn less fuel per seat per mile. And for 60 years, the fundamental shape of a commercial airplane hasn't changed. A tube with swept wings bolted underneath, the 737, the A320, the 787, the A350. They all look different in the details, but the basic geometry is identical. A cylinder with cantilever wings. Engineers have squeezed every last drop of efficiency out of this shape. Better engines, winglets, composite materials, laminar flow. Each generation shaves 1 or 2% off fuel burn, but the industry doesn't need 2%. It needs 30%, and you can't get 30% from tweaks. You need a revolution. That's where NASA came in. For decades, NASA's aeronautics division had been studying alternative wing configurations, not as science fiction, but as serious engineering. One concept kept rising to the top of every analysis: the transonic truss-braced wing. The idea is deceptively simple. If you want maximum aerodynamic efficiency, you build wings that are extremely long and extremely thin. Think of a glider. Those slender wings generate enormous lift with almost no drag. The problem is obvious: a glider weighs a few hundred pounds, a commercial jet weighs 180,000 pounds. If you make a wing that long and that thin on a jetliner, it snaps. The forces during flight, during turbulence, during landing, they'd tear it apart. Cantilever wings, the kind on every jet you've ever flown, solve this by being thick and strong at the root. But thickness creates drag, and drag burns fuel. It's a fundamental trade-off that has defined aircraft design since the 1950s. The truss-braced wing breaks that trade-off. Instead of making the wing thick enough to support itself, you add a structural brace, a long diagonal strut running from the lower fuselage up to roughly the midpoint of each wing. Like a flying buttress on a cathedral, that strut carries the bending loads, which means the wing itself can be drastically thinner. We're talking about a wing that's a fraction of the thickness of a conventional design, and because it's thinner, it generates far less drag. Because it's braced, it can also be far longer. Longer wings mean more lift distributed over more area. More lift per unit of drag means less fuel to maintain altitude and speed. To put that into perspective, the wingspan on NASA's proposed commercial version would stretch to roughly 170 feet. A 737 MAX has a wingspan of about 117 feet. The X-66A's wing would be nearly 50 feet wider. That's not an incremental change. That's a different species of airplane. But the wing is only half the story. Because the design mounts the wing high on the fuselage rather than low, it creates something engineers had been dreaming about for years. Ground clearance. Massive, unprecedented ground clearance beneath the wing. Why does that matter? Because the next generation of ultra-efficient jet engines is getting bigger, much bigger. Open fan engines, advanced geared turbofans. These power plants achieve their efficiency by moving enormous volumes of air at lower speeds. That means larger fan diameters. The problem with today's narrowbodies is that their engines already nearly scrape the ground. The 737 MAX's LEAP engines had to be mounted slightly forward and higher on the wing just to maintain clearance. There's physically no room to go bigger under a low-mounted wing. The X-66A eliminates that constraint entirely. You could hang engines under those high-mounted wings that would dwarf anything flying today. Engines so large they simply wouldn't fit on a conventional airframe. Aerodynamically brilliant, structurally elegant, propulsion ready for the next 50 years. On paper, this was the holy grail. NASA believed it. Boeing believed it. In 2023, NASA awarded Boeing a cooperative agreement worth up to $425 million to build and fly a full-scale demonstrator. Boeing would contribute hundreds of millions more. The airframe would be constructed from a modified MD-90, one of the last Douglas lineage jets ever built. They'd strip the old wings off, graft on the truss-braced wing, install new systems, and fly it by 2028 or 2029. The X-66A would be born. But here's where the story pivots, because the moment you stop looking at the wing in a wind tunnel and start looking at it parked at an airport gate, everything falls apart. Let's talk numbers. The global narrowbody market is the beating heart of commercial aviation. 737s and A320s don't make headlines like widebodies. They don't inspire documentaries, but they fly more passengers, more miles, on more routes than every other aircraft type combined, and they all operate from the same infrastructure. ICAO code C gates. That's the international standard for narrowbody operations. Maximum wingspan for a code C gate is 118 feet. Every terminal, every taxiway, every parking stand at virtually every commercial airport on Earth was built to that number. Billions of dollars of concrete, steel, and jet bridges calibrated to one dimension. The X-66A's commercial variant would need roughly 170 feet. That's 50 feet too wide. It doesn't fit, not at LAX, not at Heathrow, not at Changi, not at O'Hare, not at a single standard narrowbody gate on the planet. Why did this matter so much? Because the entire economic case for the X-66A depends on it replacing the 737 and A320 families. These are the workhorses. They fly 4 to 8 flights a day. They park at code C gates between those flights. If a replacement aircraft can't use those gates, it can't replace those airplanes. End of story. This wasn't a minor engineering detail to sort out later. This was a foundational contradiction baked into the concept from the beginning. The wing that saves 30% fuel is too wide for the gates it needs to use. But engineers aren't the type to surrender to a parking problem. They had a solution: folding wingtips. Boeing had already pioneered this on the 777X. Those massive wings fold upward at the tips, so the aircraft fits into standard widebody gates at airports. Why not apply the same idea to the X-66A's commercial descendant? Fold the outer sections of the wing after landing, taxi to the gate at 118 feet, unfold before takeoff. Problem solved. Except it's not solved, it's barely begun, because the 777X is a widebody that flies long-haul routes. It lands once, maybe twice a day. Those folding wing mechanisms cycle a handful of times every 24 hours. A narrowbody replacement flies short-haul, Dallas to Chicago, London to Madrid, Sydney to Melbourne. 4 flights a day is normal, 6 is common. 8 happens on high-frequency shuttle routes. That means those folding wing mechanisms would cycle 8 to 16 times per day, every single day. For 30 years. We're talking about heavy hydraulic actuators, reinforced hinge structures, locking pins, backup systems, and electronic monitoring, all cycling tens of thousands of times per year on an airframe that's supposed to be the cheapest thing in the sky to operate. The maintenance implications are enormous. Every actuator is an inspection item. Every hinge is a fatigue point. Every locking pin is a potential failure mode. Airlines budget narrow-body maintenance down to the dollar per flight hour. Adding a complex mechanical folding system to the most cost-sensitive aircraft category in existence isn't just inconvenient. It could be economically fatal. And then there's weight. Folding wing mechanisms aren't light. The hinges, the actuators, the structural reinforcement at the fold point, the redundant locking systems, all of that adds hundreds, potentially thousands of pounds to the airframe. Dead weight. Weight that produces no lift, carries no passengers, generates no revenue. Weight that has to be carried on every single flight, burning fuel to haul itself around the sky. Why does this matter? Because that dead weight eats directly into the 30% efficiency advantage. If the folding wing system adds enough mass, the X-66A's commercial variant might end up being only 15 or 20% more efficient than a conventional design. And at that point, an airline executive has to ask a brutal question. Why would I buy a radical, unproven, infrastructure-incompatible aircraft with folding wings and a truss I've never maintained before when I could just buy a next-generation 737 or A320 with new engines and composite wings that gives me 15% improvement with zero infrastructure changes? That question hasn't been answered, and it might never be, but the gate problem isn't even the only infrastructure crisis, because the X-66A's geometry creates a second operational nightmare that nobody talks about enough. The engines and wings are mounted high on the fuselage, beautiful for aerodynamics, terrible for ground operations. Think about what happens every time a narrowbody lands. Ground crews swarm the aircraft. Fuel trucks connect to underwing ports. Mechanics perform walk-around inspections, checking engine inlets, fan blades, leading edges. Baggage handlers work the lower cargo holds while catering trucks service the galley doors. All of this happens simultaneously in 25 minutes or less. That 25-minute turnaround is sacred. It's the foundation of low-cost carrier economics. Ryanair, Southwest, EasyJet, Indigo, these airlines don't make money by flying fast. They make money by spending as little time on the ground as possible. Every minute at the gate is a minute not generating revenue. Their entire business model is a stopwatch. Now picture the X-66A's commercial descendant at a gate. The engines are mounted significantly higher than on a conventional narrowbody. Standard ground equipment can't reach them. Fuel ports are in unfamiliar locations. Mechanics can't visually inspect engine inlets without specialized platforms. Every airport would need new equipment, new procedures, new training, and every turnaround would take longer. How much longer? Even 5 extra minutes per turn would be devastating for a low-cost carrier flying 8 sectors a day. That's 40 minutes of lost productivity per aircraft per day. Across a fleet of 200 aircraft, that's over 130 hours of lost flying time every single day. You can do the revenue math yourself. It's catastrophic. And if low-cost carriers won't buy it, the program is dead on arrival. Why? Because low-cost carriers are the largest customers for narrow-body aircraft. They order in the hundreds. They drive production rates. They set the economic baseline for the entire narrow-body market. Lose them, and you don't have a commercially viable program. You have a science project. This brings us to the deepest, most uncomfortable question surrounding the X-66A. Even if the technology works perfectly, even if the folding wings are reliable, even if the efficiency numbers hold, can Boeing actually build it? Let's be blunt about where Boeing stands in 2024 and 2025. The company is in crisis, not a rough patch, not a downturn, a genuine existential crisis. The 737 MAX disasters killed 346 people and cost Boeing over $20 billion in direct expenses. Production quality scandals led to FAA production caps. The door plug blowout on an Alaska Airlines MAX 9 in January 2024 reignited every safety concern the public had about Boeing. The 777X is years behind schedule. The 787 production line has been plagued by quality issues. The company's credit rating has been downgraded. Workforce morale is shattered. Senior leadership has turned over multiple times. This is the company that's supposed to design, certify, and mass-produce the most radical commercial airframe in 60 years. Developing a clean-sheet commercial aircraft based on the X-66A would cost somewhere between $25 and $50 billion. That's not a typo. The 787 program cost roughly $32 billion. The A350 cost Airbus about $15 billion in development. A truss-braced wing narrowbody with folding wingtips, a high-mounted wing, new engine integration, and entirely new maintenance philosophies would be at the extreme end of that range. Boeing's current balance sheet cannot absorb that investment, not without massive government subsidies, not without a partner, and certainly not without proving to Wall Street that the concept works first. The X-66A demonstrator is step one of a 20-year journey, and Boeing might not survive long enough in its current form to take step two. And then there's the timeline trap. The X-66A demonstrator isn't expected to fly until 2028 at the earliest. Some industry insiders think 2029 or 2030 is more realistic given Boeing's track record with program timelines. After the demonstrator flies, Boeing would need to analyze flight data for years, then design a production-ready commercial variant, then build a supply chain from scratch because nothing about this aircraft uses standard narrowbody tooling, then certify it with the FAA, EASA, and every other regulatory authority, then begin production. A realistic entry into service date for a commercial truss-braced wing narrowbody, late 2030s at the absolute earliest, more likely the early 2040s. By then, Airbus will have delivered thousands of A321XLRs. Boeing might have a next-generation conventional narrowbody on the market. The competitive window could close before the X-66A's descendant ever carries a paying passenger. But here's the nuance: none of this means the X-66A is worthless. NASA isn't spending $425 million on a vanity project. The truss-braced wing concept generates real aerodynamic data that will inform every aircraft design for the next half-century. Even if the exact configuration never enters mass production, the research into ultra-high aspect ratio wings, into truss structural dynamics, into high-mounted propulsion integration, all of that feeds forward into whatever Boeing and Airbus eventually build to replace the 737 and A320. Think of it this way: the X-66A might be the aircraft equivalent of a concept car, a rolling laboratory that demonstrates what's possible, pushes boundaries, changes the conversation, but never parks in your driveway. The MD-90 airframe they're using as the testbed is itself a kind of poetry, the last gasp of the Douglas commercial lineage, resurrected to test the most radical wing design in modern history. Douglas built the DC-3, the airplane that made commercial aviation viable. Now its final descendant will serve as the skeleton for an experiment that could define the next era, or be quietly shelved. What's the alternative if the X-66A's commercial variant proves too radical, too expensive, or too incompatible with existing infrastructure? The industry has a fallback, and it's boring. A next-generation conventional tube and wing narrowbody, new composite fuselage, new engines, maybe an open fan design if CFM or Rolls-Royce can get the acoustics right, incremental improvements across every system, 10% here, 12% there, maybe 20 to 25% total improvement over today's best narrowbodies. It won't hit 30%, it won't be revolutionary, but it'll fit at Code C gates, it'll turn in 25 minutes. Southwest will buy 400 of them, Ryanair will buy 300, and the aviation industry will quietly admit that the net zero by 2050 target was always going to require synthetic fuels and carbon offsets, not miracle wings. That's the real tension at the heart of this story. The X-66A represents what the planet needs, a dramatic leap in efficiency, a genuine paradigm shift. But the airline industry operates on razor-thin margins, 25-minute turnarounds, and airport gates built decades ago. Physics says the truss-braced wing works. Economics says the airline business might not let it. The X-66A is the most promising and most contradictory aircraft in a generation. It could save the industry billions in fuel, it could slash emissions by a third, it could redefine what an airplane looks like for the next century, or it could end up in a museum next to every other beautiful idea that couldn't survive contact with the real world. The question isn't whether the wing works, the question is whether the world will change its gates to match. What do you think? Should airports be rebuilt around a better airplane? Or should airplanes keep being built around old airports? Hey, before you go, the YouTube algorithm thinks you're going to like this video next, so why not check it out?